In this episode, we're going to take a very practical slice of data protection and make it feel concrete, protecting training and test data so it stays confidential, controlled, and trustworthy. For AI systems, training data is the material that shapes what the model learns, and test data is the material you rely on to judge whether the model behaves acceptably. If either one is exposed, you can create privacy harm, compliance violations, and loss of trust, and if either one is tampered with, you can create misleading results and unsafe behavior that survives into production. Beginners often assume that data protection is mostly a technical job done by a storage system somewhere. But the reality is that protection is a combination of access control, secure storage practices, ownership, and repeatable routines that prevent accidental exposure. Access control determines who can see or change the data, and secure storage determines where the data lives, how it is protected at rest, and how it is copied and retained. By the end, you should understand why training and test data are special, how access control reduces risk, how secure storage reduces exposure, and what high-level practices keep these controls effective over time. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A helpful first step is understanding why training and test data deserve special attention compared to ordinary operational data. Training data is often large, aggregated from many sources, and used in environments where multiple people and tools interact with it, which increases exposure risk. It can also contain sensitive information that was not obvious, such as identifiers embedded in text, internal details in documents, or patterns that reveal more than intended. Test data is often treated as harmless because it is used for evaluation, but test data can contain the same sensitivity as training data and can also be misused if it leaks. Another reason test data matters is that it must remain separated from training to support honest evaluation, and if access control is sloppy, people may accidentally reuse test data in ways that invalidate results. Beginners should also recognize that the value of training data can attract attention from competitors or malicious actors because it can reflect proprietary knowledge and unique business context. In other words, this data is both sensitive and valuable, which makes it a high priority to protect. When you treat training and test data as core assets, you build the foundation for trustworthy AI outcomes. Access control is the first major protection because it reduces the number of people and systems that can expose or modify the data. Access control is not just a login gate. It is the set of rules that determines who can read data, who can write data, who can export data, and who can share data. In a mature program, access control is tied to roles, meaning people get access because of job responsibilities rather than because they asked nicely or because they are part of a general team. Beginners often assume that if someone is on the AI project, they need full access to all datasets, but that is rarely true. Some people may need access to evaluate output quality without seeing raw sensitive data, while others may need access to manage storage without being able to export content. This is where least privilege becomes a practical principle, because it limits blast radius when mistakes occur. Access control also supports accountability because it becomes possible to trace who accessed what and when. When access is disciplined, leakage becomes harder and tampering becomes more detectable. Role design is an important part of access control because roles reflect real work responsibilities and make permissions manageable at scale. A role might be data steward, meaning responsible for data quality, provenance, and approvals, or it might be model trainer, meaning responsible for running training processes, but not necessarily for selecting data sources. Another role might be evaluator, meaning responsible for testing and validation, and another might be operator, meaning responsible for monitoring production behavior. Beginners should understand that roles are not about hierarchy. They are about separating responsibilities to reduce risk. If one person can select data, modify data, run training, and approve deployment alone, the organization has a single point of failure. Role separation supports integrity by reducing the chance of unnoticed tampering and supports confidentiality by limiting exposure. Role design also supports evidence because you can show that access is aligned with defined responsibilities. In practice, role design should match the organization's size and structure, but the principle remains the same. Access should be granted intentionally and narrowly. When role design is clear, access decisions become consistent instead of ad hoc. Access control also needs lifecycle management, because permissions that remain after someone changes roles are a common cause of exposure. Training projects often involve contractors, temporary team members, and cross-functional participants, which increases the risk of orphaned access. Lifecycle management means access is granted with a clear reason, reviewed periodically, and removed when the reason no longer exists. Beginners sometimes assume removal is automatic, but it often is not unless the organization has disciplined routines. A mature program performs access reviews, especially for high-sensitivity datasets, to confirm that everyone with access still needs it. It also defines what approvals are required to grant access, particularly when data contains personal information or confidential business content. Another important aspect is limiting export and sharing, because data that can be exported freely can leak easily even when access is restricted. Access control, therefore, includes not only who can read data, but also what actions can be performed on it. When access is reviewed and controlled over time, the program stays safe even as teams and projects change. Secure storage is the second major protection, and it begins with the idea that not all storage locations provide the same level of control. Secure storage means the data is stored in a location where access can be managed, where activity can be logged, where retention can be enforced, and where protections like encryption at rest exist. Beginners often think encryption alone makes storage secure, but encryption does not prevent a user with broad access from copying data or sharing it. Secure storage is therefore about combining technical protections with governance controls, such as restricting where training and test data can be stored and prohibiting storage in uncontrolled personal locations. Another key idea is reducing copies, because data copies spread faster than policies, and each copy creates a new exposure pathway. Secure storage practices include defining authoritative sources of truth and discouraging local copies and ad hoc exports. They also include clear rules about where intermediate datasets, like cleaned or labeled versions, may be stored. When storage is disciplined, the organization can enforce consistent controls rather than chasing data across uncontrolled places. Segmentation is a secure storage concept that is especially useful in AI programs because it limits how far a breach or mistake can spread. Segmentation means separating training and test data from general shared storage, separating high-sensitivity datasets from lower-sensitivity datasets, and separating environments used for experimentation from environments used for production. Beginners should understand that segmentation is like using separate locked rooms rather than leaving everything in one big open area. If a low-risk environment is compromised or misused, segmentation prevents it from becoming a path into the most sensitive datasets. Segmentation also supports governance because it allows different access rules and monitoring rules to apply based on classification. For example, restricted datasets may require stronger access reviews and tighter retention, while lower sensitivity datasets might have broader access for experimentation. Another important benefit is that segmentation helps maintain the separation between training and test data, reducing the risk of accidental contamination that can invalidate evaluation. When segmentation is applied thoughtfully, it reduces both leakage and integrity risk by limiting pathways and reducing complexity. Secure storage also includes integrity protection because protecting against tampering is as important as protecting against exposure. Integrity protection means ensuring that datasets are not modified unexpectedly, that versions are tracked, and that changes are reviewed and approved appropriately. Beginners might assume integrity is only a concern if attackers are present, but integrity can also be lost through mistakes like accidental overwrites, misapplied transformations, or inconsistent labeling updates. Version control for datasets helps because it allows teams to know which dataset was used for which training run and to reproduce results during investigation. It also helps detect unexpected changes because changes become visible events rather than silent drift. Integrity protection also includes controlling who can write to datasets and requiring approvals for significant modifications. Another crucial point is documenting transformations during data preparation, because undocumented transformations are a form of integrity loss from a governance perspective, since you cannot explain what happened. When integrity is protected, the organization can trust its evaluation results and can defend its decisions more confidently. Secure storage practices must also consider how training and test data move between environments, because movement is when leakage often occurs. Data may move from a data lake to a training environment, from a secure repository to an evaluation environment, or from internal storage to a vendor service, depending on the architecture. Each movement is a risk event because data can be copied, cached, or logged along the way. Beginners should understand that even temporary transfers can create lasting exposure if data ends up in logs, temporary files, or debugging outputs. A mature program therefore defines approved transfer methods and restricts ad hoc movement, especially for high-sensitivity datasets. It also records when data is transferred, by whom, and for what purpose, which supports evidence and incident response. Another important practice is to minimize what is transferred, such as transferring only necessary subsets rather than entire datasets. This reduces the blast radius if something goes wrong during transfer. When data movement is controlled, secure storage remains meaningful beyond a single location. The separation between training data and test data is a critical integrity concept that also has security implications, because mixed data can create misleading confidence and can hide leakage pathways. Test data should represent realistic conditions for evaluation, and it should remain protected so it is not reused in training in ways that inflate performance artificially. Beginners sometimes think mixing is harmless because better performance sounds good, but performance that is inflated by data contamination can lead to unsafe deployment decisions. Access control can support separation by limiting who can access test datasets and by restricting write access to prevent accidental modifications. Secure storage can support separation by storing training and test data in distinct areas with distinct permissions and distinct retention rules. Another important concept is controlling derived datasets, because teams often create subsets for testing, and those subsets can be copied widely if not governed. Derived datasets should inherit the sensitivity classification of the source unless proven otherwise, because they can still contain sensitive details. When separation is maintained, evaluation results are more trustworthy, and the organization can make safer decisions with better evidence. Vendor involvement introduces additional secure storage and access control considerations because the organization may not control the vendor environment the same way it controls internal storage. If training or evaluation involves external services, the program must define what data can be shared, what contractual protections exist, and what retention and deletion expectations apply. Beginners should understand that data shared with a vendor can create new exposure pathways, especially if prompts, outputs, or training data are retained for service improvement or troubleshooting. Secure storage in this context means using approved vendor environments and approved configurations that meet the organization's obligations. Access control means ensuring that only authorized internal roles can initiate data sharing and that vendor access is governed and monitored according to agreements. Another important aspect is ensuring that vendor changes are tracked, because vendor behavior changes can affect how data is stored and processed. Evidence becomes crucial here because regulators and contract partners may ask how third-party handling is controlled. When vendor data handling is treated as part of secure storage strategy, the organization reduces surprises and improves defensibility. Monitoring and evidence collection are also part of protecting training and test data, because you cannot prove protection without records that show it is being enforced. Monitoring includes tracking access patterns, detecting unusual downloads or exports, and reviewing changes to dataset permissions. It also includes monitoring integrity signals, such as unexpected dataset changes or access spikes that suggest misuse. Beginners should understand that monitoring is not about distrust of employees. It is about detecting mistakes and misuse early, because early detection reduces harm. Evidence includes access review records, approvals for sensitive data use, logs that show who accessed the data, and change records for dataset modifications. Evidence also includes documentation that shows where the data is stored, how it is classified, and what retention rules apply. When evidence is organized and tied to inventory entries, the organization can answer questions like who had access to this dataset during a given period. This supports both internal governance and external defensibility because you can demonstrate that controls were not only designed but actually used. Monitoring and evidence turn access control and secure storage into provable protections. Finally, these protections only remain effective when they are integrated into governance routines, because integration is what prevents controls from being bypassed under pressure. Intake routines ensure that datasets are inventoried and classified before they are used for training or testing. Approval checkpoints ensure that sensitive datasets are used only with appropriate sign-off and that storage locations are approved. Change control routines ensure that new data sources and new transfers are reviewed and that inventory and classification are updated accordingly. Periodic review routines ensure that access permissions remain appropriate and that data is not quietly copied into uncontrolled storage. Beginners should recognize that this integration is what makes protection consistent across teams, because it prevents each project from inventing its own approach. It also reduces last-minute chaos because evidence is produced continuously rather than collected in a rush. When access control and secure storage are part of governance routines, they become normal behavior rather than special rules that people resent. This is how organizations protect data in a sustainable way. As we wrap up, protecting training and test data requires a combination of disciplined access control and secure storage practices that reduce leakage and prevent tampering across the AI lifecycle. Training and test data deserve special attention because they are often aggregated, sensitive, valuable, and used in environments where many people and tools interact with them. Access control reduces risk by granting permissions based on defined roles, applying least privilege, reviewing access over time, and restricting export and sharing. Secure storage reduces exposure by using controlled storage locations, minimizing copies, segmenting sensitive datasets and environments, and protecting integrity through version discipline and controlled modifications. Controlled data movement, separation between training and test data, and careful handling of vendor involvement prevent common pathways for leakage and contamination. Monitoring and evidence collection make protections provable and support fast response when anomalies appear. When these protections are integrated into governance routines like intake, approval checkpoints, change control, and periodic review, they remain effective even as projects evolve. For a new learner, the key insight is that data protection is not a single tool. It is a consistent system of boundaries and habits that keeps training and test data both confidential and trustworthy.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.